Hello geometry students, and welcome to a video on dilations. These are dilations in the coordinate plane. We can also do dilations in synthetic geometry, but this lesson is entirely in the coordinate plane, so you have the XY axis to help you. Okay, so first of all, what is a dilation? A dilation, like your pupil dilating, you think of your pupil getting bigger, but in truth a dilation is something getting bigger or smaller. It's just a change in size without changing the shape. Okay, so it's going to be the enlargement or reduction. Enlargement or reduction of a figure. Notice nothing here about it changing its shape, just getting bigger or smaller. So because it's changing its size, it's still considered not to be an isometry. This is different from reflections, rotations, and translations because this is a change in size. And those other three, those are the isometries, which are not a change in size or shape. Okay, so a dilation. So this is also the scale factor is the term that we use to determine how much the size has changed. And we usually use the letter K, not always, but usually use the letter K for the scale factor. And when K is greater than 1, so when K is greater than 1, then you're going to get an enlargement. The dilation is an enlargement. And when K is less than 1, then you're going to get a reduction. Okay, what if K equals 1? Well, if K equals 1, then it's not going to change the size, that's all. So we wouldn't even consider that a dilation. Okay, I'm going to do number 1. Now, I'm not going to do all of these, but you have to do whatever I don't do. So I'm going to complete number 1 for you right now. So let's take a look at what we have, the first example. And we're going to do what we always do, which is we're going to start by graphing the pre-image. Let's just graph triangle RST. Okay, so there's our pre-image, and I'm just going to shade it as we usually do. So there's our pre-image. Now, you might have noticed that these graphs, the grids that were given for these problems, these graphs go from -10 to 10. So the squares are a little bit smaller, makes it a little bit harder. You got to be more careful when you count. That's because sometimes when we dilate, things are going to get so big that we need a more space than we had before. So instead of going from -8 to 8, we're using scales that go from -10 to 10. Okay, so what does this mean? How are we going to apply this rule? And all that means is we're going to multiply all of the xy's by 2. So in terms of a transformation rule, what this means is that all of our xy's will go to 2x times 2y. Comma 2y. 2x, comma 2y, just like that. That's what it means. That's what the k equals 2 means. It's pretty simple to apply. It just means we multiply everything by 2. So if r started at -5, 1, multiply that by 2, we get -10. Multiply that by 2, we get 2. If s started with -3, 4, it's going to go to -6, 8. And if t started at 2, -1, it's going to go to 4, -2. And that's pretty much all there is to it. Now let's see what the graph looks like. Now this is going to be a dilation from the center. So it's kind of like it's expanding from the center, from the origin. So let's go ahead and plot those points. Okay, so there's the dilated image. Now a couple things. When you do reflections, translations, rotations, it's easy to check it with patty paper. So how can we really check this? There's really no patty paper or what do they call it? Tracing paper. There's no tracing paper that you can use to help you with this, but what you can do is you can kind of look at all of the segments, and all of the segments should still be parallel. So when you look closely at this, you can see that the segment that's been dilated to be twice as long is parallel to the original segment. The same thing here, S prime, T prime, that side of the triangle is also parallel, and it's harder to tell with the shorter segment, but that one is also parallel. Just a little thing to look at to make sure that you're doing these right. I think after doing this, and what I'm going to do from now on is I'm going to not shade the original, I'm only going to shade the image instead of the pre-image. So let's go on to the next example. Okay, so the next example that I'm going to show you, notice that k is now a fraction. It's now less than 1, which means we're going to start out with a larger image, and it's going to now be reduced to a smaller size. So we'll see how that kind of dilation works. So let's go ahead and start by graphing the triangle with vertices w, x, y. Okay, so there's our pre-image. And remember that with a 1/4, it means it's going to get smaller this time. And that means we multiply all of the numbers in here by 1/4. So our transformation rule in this case would be xy goes to 1/4 x, 1/4 y. All right, let's go ahead and see what we get. Now, when we multiply these, don't be too intimidated by fractions. We're going to get nice numbers most of the time. We might get decimals, but they're going to be like 0.5. They're not going to be like 0.374 or something like that. Okay, so let's see what we get. 1/4 of -4, that's -1. 1/4 of 8, 1/4 of 8 is 2. Okay? 1/4 of 10, a quarter of 10 is 2.5. You can use a calculator, by the way, and just put 0.25 times 10 if you want, 0.25 times 4, whatever. So 1/4 of 0 is, of course, 0. Doesn't matter what fraction we take of 0. 1/4 of -2, 1/4 of 2 is half, so 1/4 of -2 is -0.5. And 1/4 of 8 is 2, so 1/4 of -8, -2. Okay, let's plot those points, see what we get. So we have -1, 2, right there. There's our w prime. We have 2.50, that's right about there. That's our x prime. And we have -0.5, -2 right about there. And there's our y prime. Now it's a little bit harder to tell, but like I told you before, once you get your dilation figured out and plotted, all of the sides will be parallel to what you started with. So the pre-image sides and the image sides will maintain their parallelism. So you can kind of look at it and see that that's happening here. And now let's go ahead and shade our image. Just shade the image. Okay, there's the next example. Okay, let's go on to number 5. That's going to be our next example. Okay, so we're doing this one just because, for one, the scale on the xy plane, this is our x-axis, and this is our y-axis, just a little bit different, right? It's not at the center, so I just wanted you to be prepared for that. And then our multiplier, or our scale factor, this time, this is greater than 1. So it's not less than 1. We expect this to get larger, but by 5/2, which is actually 2.5. So you can use decimals, or you can use fractions for this either way. Okay, let's go ahead and plot our pre-image, which is this time is a square. All right, so there's our pre-image square, and when we dilate it by the scale factor of 5/2, we're just going to get another square that just kind of blows up from the origin. So you can think of it kind of like a balloon blowing up. So when I multiply 0 times 5/2, nothing happens to that one. So that point's actually not going to go anywhere with the dilation. When I multiply 2 by 5/2, you can think of it like this. So 2 times 5/2. And the 2's cancel and you just get 5, right? That's nice and easy. What if you multiply 4 times 5/2? So we have 4 times 5/2. Well, the 2's cancel with the 4, right? So this cancels to give you a 2. So it's 2 times 5, and that's actually 10. So the 4 is going to expand to 10. 6 times 2/5. I'm going to write it over here. So we have 6, not 2/5, but 5/2. Here, the 2 cancels, and we get 3 times 5, which is 3 times 5 is 15. So we get 15 there. And then the 5/2 times 2, that one's we already did that, right? When we multiplied 2 times 5/2, we did it here, we did the same thing. So we're going to just get 5. All right, let's do that for our last point, G. And we've actually already done 4 times 5/2 right there. So it's still going to be the same thing, which is 10. So that's 10. And then -2 times 5/2. The 2's cancel, but you keep the negative, so you just get -5. All right, you got to be careful with these fractions and these negatives, but those are the points of the dilation. So let's go ahead and graph the transformed image just by plotting those points. All right, and there is our dilated image. This one's kind of cool because when it does dilate from the origin and one of the points is already on there, you get this sort of smaller image expanded out like that. And if you think about it, each one of these sides, if you were to measure this, I guess it's hard because it's slanted, but if this is 5 units, then this would be, I don't know if it is, but that would be 5 halves. That would be 2.5 times as far. Okay, so there we go. And you can see the parallel rule still applies here, even though these are the same line. It's still going the same direction. Okay, we're going to skip down to number 11 now, because number 11 we're asked to actually go backwards. We already have the pre-image, see the D's that are not primed, and we have the image, and we need to figure out now what was the scale factor that was used there. So how are we going to do that? So what we're going to do is we're just going to write down the points of the pre-image and the image. So we know that D is at 0, 2, 4, 6. So D is at 0, 6, and D prime is at 0, 2. Now, all you ever really need is just one point like that, but I know that some of you might already be thinking about it, and that's great. Remember, it's getting smaller, right? It goes from the larger to the smaller, so think of it as a fraction. You can always think of which direction it will go in like that. But let's just get another point, too, just to make sure. Let's get F, because it's not on one of the axes. So F is at -2, -1. And that's F prime. And F was at -1, 2, 3, 4, 5, 6, -3. So 6, -3, that's our F. Didn't leave much space there because I put the F prime a little too close, but that's okay. All right, now what are we looking at here? We're looking at what the scale factor going from D to D prime. So it got smaller, right? So we expect a fraction. So we have to go with the final image over the image. And that's really all you need to do here. So 0 over 0, you can't get any information from that. But 2 over 6 you can get, right? 2 over 6 reduces to 1 over 3. And here you have it again, -2. This is a negative right here. This F is negative. So -2 over -6 is also 1/3. And -1 over -3 is also 1/3. There you go. I mean, it's always going to be the same thing. It's always going to be the same K. Once you find it once, you don't really need to do all these times. But it's kind of a good idea to check your work and make sure you're getting the right answer. So the scale factor is 1/3. Remember, it got smaller, so we have to use the fractional scale factor. Don't make it too difficult or too complicated of which way to go, whether it's 3 over 1 or 1 over 3. It's getting smaller, so it's 1/3. Okay, that's probably the easiest way to think about it. Let's try this one. I'm going to pause the video and let you give it a shot. I'm just going to write down a couple ordered pairs, and you should too. Okay, so there's a couple of values, and I'm just going to go back to this one. I'm just going to write that this is a reduction. You need to identify that it's a reduction, which means that K is going to be less than 0. You need to kind of think that through, because going from D to D prime, it's clearly getting smaller. This one, on the other hand, going from the non-primes to the prime, it's getting bigger. So this is an enlargement, which means K must be greater than 0. So we know what we're looking for, and we just have to decide, are we going to go this over this or this over this? And that's really it. And you can do that for any point, and it should be the same, any coordinate. So I'm going to go -8 over -2. And that's 4. I can try this one, +8 over 2, that's 4. I can go -8 over -2, that's 4. 4 over 1, that's 4. They all check out. Scale factor, oops, 4 over 1 isn't 1, it's 4. Scale factor is 4. And that's it. Okay, hope you found this video helpful.